Hello, my name is Ashish Udgave. I am working as Assistant Professor in Department of Mechanical Engineering, Sharad Institute of Technology College of Engineering, Yadra, Itsalganji. I am welcome to all in the lecture of Work, Power and Energy. In last video, we have covered concept of law of conservation of momentum and problems on pile and hammer. Today, in video number 14, we are going to cover virtual work method and problems on virtual work method. Virtual work method. We already saw the application of Newtonian mechanics to many engineering mechanics problems. There were many scientists before and after Newton who found solutions to mechanics problems by completely different approach. Jean Bernoulli and Leonardo da Vinci are the names associated with this school of thought. They imagined a small displacement of bodies and found out the work done by various forces in the system and said if the body is in equilibrium, then total work done by the system should be zero. This approach is called virtual work method. The word virtual is used since in reality there is no actual displacement. The term virtual is defined by Webster as being in essence of effect but not in fact. The work done is virtual if displacements are virtual or forces acting are virtual. Hence, in virtual work approach, we may have following two approaches. Number one, principle of virtual displacements, and number second, principle of virtual forces. In this chapter, we consider the principle of virtual displacements only. Work done by forces and movements. We know that work done by force is equal to force into distance moved in direction of force. In this figure, various forces acting on a particle are shown. If the particle moves a distance s in x direction from point A to B, then work done by various forces are as given below. Work done by force P1 is equal to P1 into S. Since force P1 and displacement S both are in same direction, therefore work done is equal to force multiplied by displacement is equal to P1 into S. Now work done by force P2 is equal to, since P2 is acting towards left direction and displacement is in right direction, therefore there is minus sign. Therefore work done by force P2 is equal to minus P2 into S. Now work done by force P3, since there is no displacement, therefore work done by force P3 is equal to 0, and force P4 is force inclined at an angle theta with respect to x axis. Therefore by resolving it towards into two components, we get P4 cos of theta and P4 sin of theta. The work done by force P4 sin theta is equal to 0, and work done by force P4 cos theta is equal to P4 cos theta multiplied by S. Since P4 cos theta and displacement both are acting in same direction, therefore work done by force P4 is equal to P4S into cos of theta. Similarly, if the particle moves from A to C in vertical direction, then work done by various forces is as given below. Now, work done by force P1 and P2, since displacement is in vertically upward direction and force P1 and P2 both are in horizontal right and left direction respectively, therefore work done by force P1 and P2 must be 0. Now work done by force P3, since P3 is acting in vertically upward direction and displacement also in vertically upward direction, and therefore work done by force P3 is equal to P3 into S dash, and work done by force P4 is equal to P4 sin of theta multiplied by S dash. Since P4 sin theta and S dash both are acting in same direction, therefore work done by force P4 is equal to P4 S dash sin of theta. On the same lines, we can say work done by movements is equal to product of movement and the angular rotation in the direction of movement. Since in the left figure, that is figure A, movements m1 and m2 and m3 are acting on a body which rotates by an angle theta as shown in figure B. Then work done by various movements are as given below. Work done by movement m1, since m1 is acting in a clockwise direction and body also acting rotating in a clockwise direction, therefore there is positive sign. Therefore work done by movement is equal to m1 into theta. Work done by movement m2, since m2 is acting in anti-clockwise direction and body is rotating in clockwise direction, therefore work done by movement m2 is equal to minus m2 into theta. And work done by movement m3, since m3 is rotating in clockwise direction and body also rotating in clockwise direction at an angle theta, therefore work done by movement m3 is equal to m3 into theta. Number 1. No work is done by a force if displacement is at right angles to the line of action of force. Number 2. Work done is negative if displacement is in direction opposite to the force. And number 3. Work done by movement is negative if rotation is opposite to the direction of movement. The method consists of following steps. Number 1. Give an elemental virtual displacement to the body in equilibrium to suitable direction. Number 2. Write down the work done by each force in the system. Number 3. Sum up to get total work done by a system of forces and equate it to 0 to get required equations. Many times such equations are identical to the equations of equilibrium. However, the method of getting these equations is completely different in this method. A number of problems are solved to explain and to illustrate the virtual work method. Sign conventions. In this chapter, the positive senses of movements and displacements are given below. Number 1. Forces and displacement are positive if they are in positive direction of coordinates as shown in figure. Number 2. Movements and rotation are positive if they are in clockwise directions. First problem. Determine the resultant of system of concurrent forces acting on a body as shown in figure A. Let E be the equilibrium of the system which makes anticlockwise angle theta with x-axis. Then the system is in equilibrium with force F. Let us give a virtual displacement of delta x in x direction as shown in previous figure B. Now resolving all these three inclined forces in x direction and y direction, and then total virtual work done by a system of forces is given 50 into cos of 45 into delta x plus 80 into cos of 25 into delta x plus 70 into cos of 50 into delta x plus e into cos of theta into delta x, and equating it to 0 we get 50 cos of 45 into 50 cos of 45 plus 80 cos of 25 plus 70 cos of 50 plus e cos of theta into delta x is equal to 0. Since here all the components of forces are acting towards right direction and displacement is also in right direction, therefore for all the components there are positive signs. Since delta x is not equal to 0, therefore we get 50 into cos of 45 plus 80 into cos of 25 plus 70 into cos of 50 plus e cos of theta is equal to 0. Therefore we get minus e cos of theta is equal to 152.86 Newton. Since we will call this as the equation number 1. Now let us give virtual displacement delta y to point O as shown in previous figure C Then virtual work done by a system of forces and the equivalent are minus 50 into sine of 45 into delta y plus 80 into sine of 25 into delta y plus 70 sine of 50 into delta y plus e sine of theta into delta y, and equating it with 0 we get minus 50 sine of 45 plus 80 sine of 25 plus 70 sine of 50 plus e sine of theta into delta y is equal to 0. Since here y component of 50 Newton is acting in downward direction and displacement is in upward direction, therefore there is minus sign, and remaining all the components of forces are acting towards vertically upward direction and displacement is also in vertically upward direction, therefore there is positive sign. Since delta y is not equal to 0, therefore we get minus e sine of theta is equal to 52.07 sine of 25. Now a resultant is exactly equal but opposite of equilibrium. Therefore equation 1 and 2 can be written as r cos of theta is equal to 152.86 and r sin of theta is equal to 52.07. Therefore resultant r is equal to under root of r cos theta square plus r sin of theta square. Therefore we get r is equal to 161.48 Newton and theta is equal to tan inverse of r sin theta upon r cos theta. Therefore we get theta is equal to 18.81 degree. Therefore answer of this problem, resultant r is equal to 161.48 and direction theta is equal to 18.81 degree. Problem number 2. Determine the reactions RA and RB developed in the simply supported beam as shown in figure. Let RA and RB be the reactions at supports A and B. Let virtual displacement delta y be given to beam at point B without giving any displacement at point A. Now write down all the distances of the forces from apex point A. Therefore distance of 20 kN force from point A is 2 meter, distance of 14 kN force from point A is 4 meter, and distance of RB from point A is 6 meter, and base of triangle is 6 meter. Now displacement at 20 kN force is equal to 2 upon 6, that is distance from apex point divided by base of triangle into delta y, that is nothing but 2 upon 6 into delta y. Displacement at 40 kN force is equal to 4 upon 6 upon into delta y, and displacement at point B is equal to 6 upon 6 into delta y, that is nothing but 6 upon 6 into delta y is equal to delta y. 4 upon 6 into delta y is equal to 2 upon 3 into delta y, and 2 by 6 into delta y is equal to 1 by 3 into delta y. Now work done by force Ra is equal to force multiplied by displacement. Since displacement is 0, therefore work done by force Ra is equal to 0. Now work done by force 20 kN force. Since 20 kN is acting in downward direction and displacement is in upward direction, therefore work done by force 20 kN is equal to minus 20 into 1 by 3 into delta y. Now work done by force 40 kN is equal to, since 40 kN acting in downward direction and displacement is in upward direction, therefore work done by force 40 kN is equal to minus 40 into 2 upon 3 into delta y, and work done by force Rb is equal to, since Rb is acting in upward direction and delta y is also acting in upward direction, therefore work done by force Rb is equal to Rb into delta y. Therefore by virtual work principle, Ra into 0 minus 20 into 1 by 3 into delta y minus 40 into 2 by 3 into delta y plus Rb into delta y. Therefore we get Rb is equal to 33.33 kilonewton. Now let us give virtual displacement to beam as shown in figure C. Since body is in equilibrium, now we will give virtual displacement delta y dash at point A without giving any displacement at point B. Now write down all the displacements of all the distances of the forces from apex point B. Therefore, distance of 40 kN force from point B is equal to 2 meter. Distance of 20 kN force from point B is 4 meter. Distance of RA from point B is 6 meter, and base of triangle is 6 meter. Now displacement at 40 kN force is equal to 2 upon base of triangle 6 into delta y dash is equal to 1 by 3 into delta y dash. Now displacement at 20 kN force is equal to 4 upon base of triangle 6 into delta y dash, that is nothing but 2 upon 3 into delta y dash, and displacement at point A is equal to 6 upon base of triangle 6 into delta y dash, that is nothing but delta y dash. Therefore, now work done due to force RB is equal to, since there is no displacement, therefore work done by force RB is equal to 0. Now 40 kilonewton is acting in downward direction and displacement is in upward direction, therefore there is minus sign. Therefore work done by force 40 kilonewton is equal to minus 40 into 1 by 3 into delta y dash. Work done by force 20 kilonewton, since 20 kilonewton is acting in downward direction and displacement is in upward direction, therefore work done by force 20 kilonewton is equal to minus 20 into 2 upon 3 into delta y dash. And work done by force RA, since RA is acting in upward direction and work done and displacement is also in upward direction, therefore there is positive sign. Therefore, according to virtual work principle, we get RA into delta y dash minus 20 into 2 by 3 into delta y dash minus 40 into 1 by 3 into delta y dash plus RB into 0 is equal to 0. Therefore, we get RA is equal to 26.66 kilonewton. Therefore, answer of this problem, reaction at point A RA is equal to 26.667 kilonewton and reaction at point B RB is equal to 33.33 kilonewton. Next problem, determine the reactions in the overhanging beam as shown in figure. Let RA and RB be the reactions as shown in figure A. Let the virtual displacement delta y be given to the beam as shown in figure B. Then virtual displacement of various loads are as given in figure. Now consider figure B and write down all the distances of the respective forces from the apex point A. Therefore, distance of 20 kN force from point A is 1 meter. Distance of 60 kN force from point A is 4 meter. Distance of RB from point A is 6 meter. And distance of 30 kN force from point A is 8 meter. And base of larger triangle is 8 meter. Now, displacement at 30 kN force, displacement at 20 kN force is 1 upon base of triangle 8 into delta y, base of larger triangle 8 into delta y. Now displacement at 60 kN force is equal to base 4 upon base of larger triangle 8 into delta y. Displacement at point B is equal to 6 upon base of larger triangle 8 into delta y. And displacement at 30 kN is equal to 8 upon 8 into delta y, that is nothing but delta y. Therefore, applying virtual work principle for the beam which is in equilibrium, we get 20 into delta y upon 8 plus RA into 0 minus 60 into 4 upon 8 into delta y plus RB into 6 upon 8 into delta y minus 30 into delta y is equal to 0. Since 20 kilonewton is acting in downward direction and displacement also in downward direction, therefore there is positive sign. This work done by force Ra is equal to 0 since there is no any actual displacement or virtual displacement. 60 kilonewton is acting in downward direction and displacement is in upward direction, therefore there is minus sign. RB is acting in upward direction and displacement also in upward direction, therefore there is positive sign. And 30 kilonewton is acting in downward direction and displacement is in upward direction, therefore there is negative sign. Since delta y is not equal to 0, therefore we get RP is equal to 76.667 kilonewton. Next, let us give virtual displacement delta y dash to the beam as shown in figure C. Now write down all the distances of the respective forces from point B. Therefore distance of 60 kN force from point B is 2 meter. Distance of RA from point B is 6 meter. Distance of 20 kN force from point B is 7 meter. And distance of 30 kN force from point B is 2 meter. And base of larger triangle is 7 meter. Now displacement at 60 kN force is equal to 2 upon base of larger triangle 7 into delta y dash. Displacement at RA is equal to 6 upon 7 into delta y dash. Displacement at 20 kN is equal to 7 upon 7 into delta y dash. And displacement at 30 kN is equal to 2 upon 7 into delta y dash. 2 upon largest base of triangle is equal to 7 into delta y dash. Therefore, here 30 kilonewton is acting in downward direction and displacement also in downward direction, therefore there is positive sign. At point B there is no any displacement, therefore work done by force RB is equal to 0. 60 kilonewton is acting in downward direction and displacement is in upward direction, therefore there is minus sign. RA is acting in upward direction and displacement is also in upward direction, therefore there is positive sign. And 20 kilonewton is acting in downward direction and displacement is in upward direction, therefore there is negative sign. Therefore the displacements of various loads reactions points are as shown in figure. Therefore according to virtual work principle, minus 20 into delta y dash plus RA into 6 upon 7 into delta y dash minus 60 into 2 upon 7 into delta y dash plus RB into 0 minus 30 into minus 2 upon 7 into delta y dash is equal to 0. Since delta y dash is not equal to 0, therefore we get RA is equal to 33.337 kilonewton. Therefore answer of this problem, a reaction at point A RA is equal to 33.337 kilonewton and reaction at point B is equal to RB is equal to 76.667 kilonewton. Next problem, a simply supported beam AB of span 5 meter is subjected to a concentrated load and an external movement as shown in figure A. Determine the reaction at point B. Now in this problem we have to find reaction at point B. Therefore let the virtual displacement delta y be given at point B as shown in figure B. Now write down all the distances of the forces from apex point A. Therefore distance of 20 kilonewton force from point A is 1 meter. Distance of RB from point A is 5 meter and base of triangle is 5 meter. Now displacement at A is 0 since there is no any displacement, therefore work done by force RA is also 0. Now displacement at C is equal to 0.2 into delta y dash, that is nothing but 1 upon 5 into delta y dash is equal to 0.2 into delta y dash. Now rotation of movement 30 kilonewton force, 30 kilonewton meter is theta is equal to minus delta y dash divided by phi. Here theta is equal to, since body is rotating in anti-clockwise direction and movement is in clockwise direction, therefore there is minus sign, and theta is equal to 1 upon base of triangle is phi into delta y dash. Therefore rotation of movement 30 kN meter is theta is equal to minus delta y dash divided by phi is equal to minus 0.2 into delta y dash. Negative sign since it is anti-clockwise. Now writing virtual work equation, we get Ra into 0 minus 20 into 0.2 into delta y dash plus 30 into minus 0.2 into delta y dash delta y plus Rb into delta y. Therefore is equal to 0. Since delta y is not equal to 0, therefore we get Rb is equal to 10 kN. Next question. Determine reactions Ra in the overhanging beam as shown in figure by virtual work method. Here there is UDL between for the span of 2 meter between point A to D, and intensity of UDL is 20 kN per meter. Therefore UDL is converted into equivalent point load. Therefore total equivalent point load is equal to 40 kN, which is acting at the center of 2 meter span. Now let us give virtual displacement delta y at point A. Here reactions Ra and Rb are acting in upward direction. Now write down distances of all the forces from apex point B. Therefore distance of 40 kN from point B is equal to 4 meter. Distance of Ra from point B is 5 meter, and distance of 20 kN from point B is 1 meter. Let us give virtual displacement delta y at A as shown in figure P. Therefore displacement at A is delta y, displacement at D is 3 by 5 into delta y is equal to 0.6 into delta y. Therefore displacement at centroid of UDL is equal to delta y plus 0.6 into delta y divided by 2 is equal to 0.8 into delta y, and displacement at B is equal to 0. Displacement at C is minus 1 upon 5 into delta y is equal to minus 0.2 into delta y, and rotation of movement is equal to delta y upon 5 is equal to 0.2 into delta y. That is nothing but 1 upon base of triangle phi into delta y. Since here movement is clockwise and displacement also clockwise, therefore there is positive sign. Now writing the virtual work equation for the system, we get Ra into delta y minus 20 into 2 into 0.8 delta y plus 40 into 0.2 into delta y plus Rb into 0 minus 20 into minus 0.2 into delta y is equal to 0. Since delta y is not equal to 0, therefore we get Ra is equal to 20 kN. Therefore answer of this problem, a reaction at point A is equal to 20 kN. Please note that this video is prepared for academic use only. To understand the concept of virtual work method and to solve the problems on virtual work method for UG students only. Thank you. Thanks a lot. For any query, please feel free to contact me on mail or on mobile. Thank you.